Hi everyone, today I'm going to present our paper V3D SLAM Robust RGB-D SLAM in Dynamic Environments with 3D Semantic Geometry Voting. I'm Ken, I'm from the Learning and Adaptive Robotics Lab at the University of Texas at Arlington. So one of the long-lasting standing problem in Visual SLAM or in RGB-D SLAM particularly, that is we haven't really well considered the movement of the object in dynamic scenes. For example, we have moving objects as a person who is walking around in the room. And the second example is that we have a person who is sitting or standing at one position and tilting their head while they're talking to each other. So we identify these as moving and partially moving objects respectively. So to solve this problem or to tackle this problem efficiently in the context of robot perception, we realize that a voting mechanism must be defined with the perception of the robot. In this work, we focus on the RGB-D perception. So the main objective of our paper is to identify whether the object is static, or is it moving, or is it partially moving in a dynamic scenes, as we mentioned before. To do this work, we realize some problems or some challenges that we have to deal with in the context of this paper. First challenge is the moving camera. So for example, we have the camera mounting on the robot. When the robot moves inside the room or in the indoor environment, we also know that the camera is moving with the robot. So it's hard to identify which object is static or which object is moving when the robot is moving. The second challenge is that moving objects in the scenes. For example, if we have any objects that moves at the same direction and same velocity as the robot, it's hard for the robot to know that object is static from its perspective, or is it really a moving object. And thirdly, we have to also deal with the intra-moving objects as we discussed, how to identify a person who is tilting the head while talking or waving their hands at each other in the dynamic scenes. So the fundamental questions right here is to differentiate between static and intra-moving and then moving objects, and we can extend this question into the context of moving cameras. So to tackle this problem efficiently, we propose a voting mechanism based on huge voting for dynamic objects. So first of all, we will calculate pairwise distances between objects in the scenes. So first of all, we will segment that those objects represented in the scenes and project into depth maps to see their perception, and then compute the pairwise distance between the bounding boxes of the objects. So for example, we will calculate these pairwise distances in the frame that is t minus 1, and then we also calculate the similar distance in our current frame, so which takes t minus 1 and t frame in the algorithm. So then we compute the accumulator array for 2 frames based on the object keys. So when it comes to object keys, we also tracking the object in the scene. So for example, we have the person is moving within the frame t. This person or this object ID will be kept track until the end of the sequence. So based on the object ID, we will know is there pairwise distance relation to other objects in the scenes. Then we will do the threshold on the accumulator array to vote for dynamic objects. So we will have or define a threshold for moving objects. So for example, if that object relates to other entities in the scenes and it exceeds a certain threshold, for example, this object and this person, we will identify those as moving objects. Then we also separate intra-moving objects and moving objects in based on the chamfer distance. Particularly, chamfer distance is to compute the distance between point clouds. So if this person's chamfer distance is lower than a threshold for chamfer, we will identify it as a intra-moving object. For this person, the chamfer distance will be larger than our threshold, so we will still identify these as the moving objects. So that is the whole idea of huge voting for dynamic objects. So once we have these moving and intra-moving objects, we can keep the intra-moving objects in the play while removing the moving objects from the scenes to reconstruct the 3D scenes or give the robots more precise perception for performing RGB-D slam. So to evaluate our mechanism on other dataset, we choose the term RGB-D dataset to evaluate our result on and have the online tool for verify our result. In this dataset, we compare the absolute trajectory error and then the relative pose error against other prior VSLAM methods in this RAM. We compare it with 6 other state-of-the-art techniques in this research, and relatively we have achieved better result compared to those before in both relative pose error, which are for translational drift and then rotational drift. These metrics represent for the error when the camera moving forward or moving sideways, or it rotates to have the perception or obtain more frames of the scenes. So in both of these errors, we achieve relatively good result compared to the most recent technique, which is the CFP slam. So we also choose the CFP slam as the method to compare against the qualitative results. So for the second and the third and the fourth one is for the result from CFP slam, and the first and the third row represent our result, qualitative result on the RGB-D thumb dataset on 8 sequences. So first, we achieve relatively the same trajectory as CFP slam does. However, for some sequence we also not really well performed. For example, the static and the RPY sequences, we have relatively more errors compared to the graph truth. So to verify the robustness and the correctness of our techniques in the real world on a real robot, we have a demo here for the robot to move in an indoor environment while there is a person walking by in front of its perception or its observation, and it effectively removes all the fragments or identify the moving object very precisely to reproduce the scenes that without the person moving by itself. So this is the result sequence that the robot can produce, and it also has the camera trajectory estimation, which are colored in the orange frostum and the red line. So that's it for the real robot demo, and I think that's the end of the presentation. I'm really thankful for listening.